So I am Jeff Smoley, infrastructure architect at NativeX. I've been doing software development for over 13 years, and I've been with NativeX for about 4 years.
And I'm Derek Bromenshenkel, one of the other architects. I've been with NativeX for about 4.5 years. Before that, I was at IBM working on WebSphere, and I joined the infrastructure group working on Cassandra at NativeX about 1.5 years ago.
So what we plan to go over today is a little bit about NativeX and what we do, why we chose Cassandra, some of the challenges that brought up, things like auto ID generation, a little bit about FluentCassandra, some stuff about Hector, which is the Java client, IKVM.net, HectorNet, and then our reporting infrastructure, how we sort of tied that into Cassandra. So again, our company is called NativeX. It was formerly named W3I. Our office is in Sartell, Minnesota, which is about 75 miles northwest of Minneapolis. We have remote offices in Minneapolis and here in San Francisco, and we employ about 150 employees. So what do we do? We're a marketing technology platform that enables developers to build successful businesses around their applications. So we do essentially app distribution, both on the desktop and in the mobile. We provide publishers with a way to monetize and advertisers with a way to gain distribution. Some metrics about our mobile business, which is where we really have the challenge of scaling. We have over 700 million unique devices in our network. We have thousands of apps that we serve to those devices. We have over 100 million monthly active users and over 200 gigabytes of data that we ingest per week. Just a little bit of backstory of sort of where we came from and why we needed to have a scalable solution. So we went from doing about 100 million sessions per quarter in the mobile business to up to 5 billion a quarter. And we anticipate by the end of quarter 2, we'll have over 7 billion sessions that we've produced. This growth was, of course, anticipated, and as you can see in this graph, it just sort of shows that that sort of exponential growth that we've been having quarter over quarter. And this is going to continue to happen as we branch out and get more visibility. And so, this made us realize that we needed to have the infrastructure scale at the same rate as the business in a linear fashion. So our original architecture was built all on top of Microsoft SQL Server. Again, we're using .NET as the web application code, but the backend really was using a Microsoft SQL Server, which was just a 2-node cluster, an active-passive setup. So it was really one node serving all of the requests to the database, and the second node there was just for failover reasons. That machine had about 12 cores and 192 gigabytes of memory. And then that all sat on top of our compellent SAN, which is a 172 tiered disks setup with some SSDs, fiber channel disks, and SATA. But again, this is a very vertical, monolithic approach. The only way to really scale this was by adding more hardware to this one machine. And we eventually got to the point where you just couldn't add any more to it without going into something like a supercomputer or whatever. And so it just wasn't really scaling with the growth of our business. So we set out to achieve a couple of objectives. We needed to have that horizontal scale where we could add more of the same, adding additional nodes of like hardware so that we could spread out that load. And that also would give us an incremental cost structure. So not only can we add more machines, but we know exactly how much that's going to cost. With a vertical scale, it's a different amount of money every time you want to scale. It might be a little bit of memory one time and more CPU the next, and some more disks, here and there. with this structure, we can have an incremental cost. The other thing that we're sort of after as a side benefit was resiliency, so that we had a no single point of failure, with not just in a single data center, but across multiple data centers, so that we could be geographically distributed, so that if at some point we wanted to be in a second data center and have the ability for one of those data centers to go down and still run the business, we could achieve that. So we were looking for a product that would provide that flexibility. So that really led us into looking at NoSQL solutions. And at the time, we really didn't understand what that meant. So we did some research and found out that the term actually stands for not only SQL. So SQL, being a declarative language, is really agnostic of technology. It's just a way to express some set of requirements and then get some result back from that. And so the SQL language itself is still valid in the NoSQL world. So really, NoSQL is about understanding problems and focusing on solutions. Each product really solves a very specific problem. So it's not about silver bullets and black boxes. And what I mean by black boxes is you don't just stand these things up and they magically work. That's sort of where the relational mindset came from, is you just stand up the relational database, maybe some DBA does a few things here and there, and it just works. You don't care about the underlying architecture. You don't care how it reads and writes from the disk. You don't care about how it caches memory, things into memory. You might know a little bit about those things, but in most cases, you're not really worried about that stuff. NoSQL is really about understanding those things and really learning about how they actually achieve those, because that helps you design your systems to exploit those features. So again, it's about using the right tool for the right problem. So in our research of different products, so we decided we wanted to choose an existing product. We didn't really want to build out a system by hand. And so we did a bunch of research, and the things we were looking for were things like distributed and shared nothing. Again, we wanted multi-cluster support for things we may do in the future to be in multiple data centers. We wanted something that was mature, but also popular. Something that a lot of different companies were using, but also something that not only a lot of companies are using, but is fairly well into its development cycle and has some major features to it. Documentation was a big thing for us too. As we did some research, we ran across some products that there just wasn't any documentation or very sparse documentation. And then the last thing, because had all of our code built in .NET, we needed something that actually supported .NET from a driver standpoint. So this led us into Cassandra. Ultimately, we chose Cassandra. And the reason we chose Cassandra is because it is multi-node. Again, each one of these little blue circles on the graph on the diagram on the left side where it says DC1, each one of those blue circles represents an independent node. It has all of its own hardware, its own memory, CPU, and disk. None of it's shared between each node. We also wanted multi-cluster, which is provided in Cassandra. So you see here you have two data centers, data center 1 and 2 in the blue and the green. And so it allows you to offload work across multiple data centers. It's also highly available. So you use replica sets, which you see here with the white boxes that say R1, R2, and R3. You can replicate data around the ring so that if a node goes down, you still have the ability to get data off that and put data onto to those other nodes. And you can choose your replication factor. A typical standard to use is 3, and I'll explain a little bit why you would want to use 3 in a minute here. It's also durable, so data is written to each of the nodes, and it's actually written to a commit log so that if one of the nodes goes down, you still have that data and you can replay those transactions. There's also coordinator nodes that you actually communicate with, which can be any node in the ring, that will also do some things like hinted handoffs and whatnot, so that when nodes go down and come back up, they can get the data that they missed. And so the other thing, like I mentioned, is shared nothing. Again, none of the hardware is actually shared between each of these nodes. If you're running this in Amazon, then you have other situations there where there might be some shared hardware, but the idea here is to minimize sharing that hardware. And even the software part of it too. Each node is running the code independently. And so the last thing that really struck us with Cassandra is that it has tunable consistency. So like Jonathan Ellison mentioned this morning is, it's eventually consistent, but it has the ability to sort of tune that based off of your needs. And so the idea here is that, let's say I have something I want to write to the node. I can choose a consistency level of 1, and that data will come from the client. The client will choose one of the nodes as a coordinator and send that data over to all the replicas. So if we have 3 replicas here, you can see that it's actually writing, which is the blue arrows, to those 3 replicas. The minute one of those replicas responds, the coordinator will actually respond back to the client and say, hey, we actually got this data put into the cluster, if you're choosing consistency level of 1. And so then the same thing goes for the read. As soon as one of the nodes actually responds with the data, it will return that. Now, if you choose a consistency level of 1 for both the read and the write, you may actually get slightly inconsistent data because that data may have reached one of the nodes, in the example here, node 1, let's say, and your read is actually hitting node 7, you might get the wrong answer. That all depends on your application, though. That somewhat wrong answer may not actually be the wrong answer for that period of time. It just depends upon what level of consistency you need. Now, if you do need a little bit more consistent, where you want to make sure what's written when it comes back that you actually get the right answer, you can do what's called a local quorum, or quorum in general. And so what you're after there is you're trying to make sure that the majority of the nodes are responding. So again, in a replication factor of 3, you would want 2 of those nodes to respond with the answer. So let's say, again, that we come in from the client, we're connecting to node 10 here, and it's going to, again, send the data to all 3 nodes. And as soon as 2 of those nodes respond, it will then take that and send that back to the client saying that, yep, a quorum has been reached, the majority of the nodes have this data, move on. And let's say immediately after that, or you have another competing thread that's coming in and needs to read that data, and it sends that over, which is going to, again, ask all 3 nodes for the data. As soon as it gets 2 of the nodes to respond, it will then compare those results from the 2 nodes, and if they don't match, it will have to wait for the 3rd node, and then from there, it can decide what the real answer is. So using quorum, you can get that consistency you want. It's still eventually consistent. You could still have a situation where a read is coming in and you haven't quite even written to the data to any of the nodes yet, but you can have that sort of, if you know that a particular record has been written, you can immediately ask for the data back and know that you're going to get the right answer back. So it allows you to choose sort of your workload. If you need to just have high performance and you don't care about the consistency, you can use a consistency level of 1. But if you need that answer back, you can be a little bit more consistent for sacrificing a little bit of performance. So again, at NativeX, what are we using Cassandra for? It wasn't a replacement database system. We didn't get rid of Microsoft SQL Server. It actually sits alongside of Cassandra. What we use the Microsoft SQL Server for is storing our configuration data, or if you want to call it master data, whatever. Basically the nouns of the application, things like offers and applications and budget rates and things of that nature. But Cassandra did solve a very specific problem for us, which was more on the transactional side. So we're writing large volumes of data quickly. We have all this activity data or event tracking data that we need to capture so that we can report off of it later. This product is very good for capturing that data quickly. But also we have very specific data that we want to pull out of large data sets. So we talked about having 700 million devices before. And we need to be able to pinpoint a very specific device and pull up its history. We need to know what that device has done in the past so that we can target the right offers to that device. And Cassandra allows for that very specific targeting of data if you model your data correctly. So Derek will now go over some of the challenges that we had and how we overcame some of those.
So as Jeff mentioned, this is just not a drop-in system for us, and you can imagine there's all kinds of things we had to overcome. So hopefully I'll be able to answer probably a lot of the questions that you have. And one of the big things there that we're starting off with is, Cassandra doesn't have an auto ID generation system, nor should it. And so you really might be asking, why are we even talking about this? Well, for us, it was a pre-existing requirement of our external web APIs. So we're kind of locked into this notion of having a unique 64-bit positive integer to identify devices and other things like that. And having an identifier that's increasing, which makes it sortable, was a plus for us. And that's really around, in our data warehouse, having clustered indexes based on these IDs. So of course, in the old way, this was done with a SQL Server identity column, and that worked great. But in this new approach, we won't be using that anymore, so we had to find something else. So Cassandra has a notion, or there's this general notion of time-based UIDs that are sortable and unique, and they're really great. We actually changed a lot of what we were using to support time-based UIDs because they're sortable, they're unique, you can generate them from any client. It's not a single point of failure. And so it's definitely the future for us. We changed our API to be backward compatible, so as time goes by, we'll be able to get away from having to generate the 64-bit integers, but for now, we needed to come up with a solution. So what are the options that we have? Well, you could really take the notion that we had before, which is just a dummy table, has one column in it. It's an identity column, and it just increment that every time you need a new ID. That'd be really easy. It'd be familiar for us, familiar for anybody that uses the SQL Server functionality. But of course, it's limited. We just got done talking about how we didn't want a single point of failure, how we wanted to be able to increase load over time. So decided against that. We worked with DataStax a lot on this project, and specifically Matt Dennis proposed a solution where we'd pre-generate a range of keys and assign them to various nodes inside the cluster. And so that makes it distributed, right? Cassandra could hold those keys. But it was a little more complicated to implement, and there was no guaranteed ordering when you did that. Another thing we found while doing our research was Instagram came up with a sharding mechanism. I got a link up there you can visit after the presentation. And it's actually really slick. I wish we could have used it. We actually ended up discovering it too late. And in reality, we weren't familiar with Postgres, and it's built on that. So, I don't think we'd have been comfortable doing it anyway. But I just thought I'd throw it out there so that you guys all know that it is something that other people have tried to solve. So what we ultimately do is chose Snowflake. It's a service built by Twitter. It's got an Apache license. They got it out on GitHub. You can take a look at it. They define it as a network service for generating unique ID numbers at high scale. It's exactly what we're looking for, right? The distributed nature and the way we need to generate a lot of these numbers. And something that really jived with us is they had the same motivation. They were going from a relational system to Cassandra, and they needed a way to solve the same problem. So just felt, we connected with that. There was a few tweaks we had to make for our Windows environment, namely different Java runtime. We had to figure out how to make it run with Apache daemon, and we removed some of the internal scribe logging. But in general, it's like out-of-the-box solution. So a few more of the technical reasons around what Snowflake does for us. So it met all the requirements that I mentioned before with being unique, positive 64-bit integers that are roughly time sortable because they're generated with a time component. and they're fast and distributed. And so those are all the requirements that we needed. And we felt really comfortable using this because, of course, Twitter had already used it in their high transaction system. It is a Java-based implementation. So you might be thinking, okay, you're a Microsoft shop. Why would you go down the Java road? And the truth is, while we do use a lot of the Microsoft stack, we're not really scared of using Java. So we were pretty comfortable in that, using that technology. Also, Snowflake uses a thrift server to actually do the communication. And while it's maybe not perfect, it's a very familiar thing with the way Cassandra does its. It uses the thrift protocol also. And so yeah, all we do is run that thrift server as a Windows service with Apache daemon. So one con that Instagram also mentioned while doing their research for Snowflake is, well, it requires Apache Zookeeper. So it's another moving piece, right? And that can be scary. But it didn't scare us, and the only reason is because it's not required on every transaction. It's only required at startup, and it basically just coordinates when each Snowflake instance starts up, it coordinates which node ID that is assigned to each individual process. And then it stays out of the workflow from there. So yes, it's a dependency, but it's very limited. It doesn't have to scale and all those things. So you might be wondering, okay, now you have Snowflake, how are you going to connect to that thing? Well, basically what we did is we built our own Snowflake client, and to eliminate web hops, the network latency, we put a Snowflake server on each node of our web servers, and then we connect to that locally from each web app. And that's the primary Snowflake instance for each one of those web apps. They don't connect to the other ones unless they need to, which is what I'll get to right now. So what happens if, say, Snowflake instance on server 3 fails? Well, what we did was implemented a round-robin failover to the other nodes, so it temporarily can ask another node for an ID. And that works really great. But the key to it really is the last point there. It automatically fails over like this, but it also automatically recovers. So if that Snowflake instance on server 3 comes back up, the app knows about that and will start using that local node again and eliminate that network latency. And we did that using what's called the circuit breaker pattern. You can research it, but it basically, when the circuit gets hot, so having a lot of failures, it trips the breaker, starts failing over to the other nodes, and it periodically can go in like a test mode where it says, okay, did Snowflake instance 3 come back up? And if it says yes, it trips the breaker back on, and you're back in business. So, okay, we met one of those big challenges that we just, outlined at the beginning. The other thing was, okay, how are we going to connect to the Cassandra cluster with our C# code? As you're probably aware, Thrift has some APIs that have generated C# code, and you could just use that. But for us and our development team, it was too low level. We needed something with CQL support, and we wanted something that had that ADO.NET or LINQ feel. And I also mentioned a need is, hey, we need something that's actively being developed to support the up-and-coming features. As you noticed this morning, there's just a lot of stuff going on with Cassandra, and we want to be able to keep up with that over time. As far as other than that, we didn't really know what we needed or wanted besides that. So through our research, we basically started with this project called FluentCassandra. And so we started the process of vetting this, like, is this going to work for us in our environment? And there's a lot of great things about it. It's open source. You can go take a look at any time. You can contribute. You can see what's going on in the guts if you're wondering how something works or if you're having a problem. Nick, the project owner, is excellent. I've had a pretty good relationship with him. He's always been very reliable and responsive to our questions. And because of his intelligence, he designed this thing for CQL up front, just knowing that that was going to be important as time went by. Another thing about Fluent is it really had that familiar feel. Like, Nick is a .NET developer, and he really designed the thing to wrap the thrift objects into .NET, types, and so it just felt a lot more familiar than some of the other choices we had. And the key thing here is, as we were doing this project migration, we were able to start our development with it and get the project rolling. Of course, once we started using it, that's when you start noticing some of the drawbacks to it. So really what we found out is it's relatively immature. There aren't a lot of users with our use case, which is a very high transaction system. And at the time we started using it, it had a pretty bad problem, which was it would permanently blacklist a node if it went down. And we couldn't deal with that. Over time, we helped them fix that, and others have contributed, and that's no longer the case. But that was a pretty big black eye for us. Another thing is, so if you had a request that failed, what happened to that? Well, it doesn't have a retry mechanism or anything like that. So basically, what would happen is just blow back up to your client, and you would have to deal with it. So what that really boils down to is we didn't want to live at those limitations. And so that really left us in a spot where we had to do something about that. But we're still committed to Fluent because, like I said, we had a great experience in our research and our initial use of it. So what we tried doing was adding resources dedicated to maturing it. But what that ultimately didn't work out. It just was taking too long, especially how this project had a timeline dedicated to it. It was distracting Jeff and myself from handling some of the other things that we had to figure out. And so that just basically left us back at the drawing board. So what does that ultimately leave us with? Well, we need more than a connector. We needed a connector with good failure tolerance is what we learned out of that. If we could just have Hector, that's what it boiled down to. It's a very popular Cassandra connector in the Java community. Tons of use cases matching ours with high transactions and wanting consistent data and multi-node, many node clusters and things like that. And after doing a lot of this research, we just realized it had really good maturity compared to some of the other stuff we were looking at. So it can auto-discover nodes, it can retry failed requests, and it can recover from failure similar to what we implemented in our Snowflake.NET client, where it can recognize a node has come back online and start using it again. You don't have to recycle app pools. You don't have to tell it that, hey, this server is okay again. But of course, it's written in Java, and that's a major roadblock for us. So I mentioned before, hey, we're not scared of using Java, but that doesn't mean we had the time and resources to rewrite our entire mobile app. So that's where you really have a problem, where Hector would be the ideal candidate, just that we didn't have the ability to use it. So Jeff is going to take over now again and talk about, all right, we're kind of at this standstill where Fluent looked promising, it has some drawbacks. We'd really like to use Hector, but we're a .NET shop, so where do we go from there?
So as Derek said, we still needed some help with this. We realized that, based off our timelines and stuff, that we weren't going to necessarily have the time to focus on that. It wasn't that we weren't capable of figuring this problem out. We just needed somebody else to sort of tackle that while we were still moving the project forward. So we ended up running into a company named Concord. They're based out of the Twin Cities, and they specialize in system, process, and data integration. So we went to them and basically told them our problem, and we asked them if they could help us mature FluentCassandra, and they came back and said, well, we have a different approach. We've used this product called IKVM.net, and we'd like to actually take the Hector assembly, the Java jar, and actually port that over to a .NET assembly. They actually had previous experience using IKVM to do this with other Java jar files and libraries and port them over to .NET. And again, they really felt that maturing FluentCassandra was just going to take way too long for the timeline that we had put in front of them. So what is IKVM.net? Or a little bit about the project, I guess. So it's an open source project. It has a main contributor who actively contributes to the project. There were even check-ins to the project in the last couple of weeks. And so it's being actively worked on. And it also has a license that allows for corporate use. So or commercial applications, corporate use, that kind of thing. So it definitely was something that we were willing to adopt or try out at least. So the meat and potatoes of IKVM.net are that it's a Java virtual machine that's actually implemented in .NET. It also has the ability to do .NET implementations of Java class libraries. And then it also comes with a set of tools that enable Java and .NET interoperability. So some use cases for this. You can actually take any old jar file and get it up and running inside of .NET using the Java virtual machine that was implemented in .NET. So it just, out of the box, you can just take, in theory, you can take any jar file and run that inside of this virtual machine. Again, another use case is that you can take your Java libraries and actually port them over to .NET, which is the route that we ended up going. Using the IKVM-C tool, you actually take that and compile your Java bytecode straight to a .NET intermediate language as an assembly file. And then sort of the final scenario, which is I'm not exactly sure if anyone would want to do this, but you could write your code in Java, compile it to the JVM bytecode, and then using the IKVM-C, produce a .NET executable out of that or in a .NET assembly. So you could literally write your application in Java if you didn't want to write it in .NET, and then run it on top of the .NET stack. In addition to that, you can actually take .NET APIs, build stubs that you can actually access through your Java code, and that way you can actually use the .NET framework from Java. So you just use the IKVM stub tool and generate these stub files that you can actually hook into your Java code. And obviously this code's not going to run or be debuggable within the Java stack, but it allows you to use the .NET framework. So again, we working with Concord, we chose their recommendation and we ported over the Hector jar into a .NET assembly. And when you do that, basically that takes all of Hector and all of its dependencies, so any other jar files it might have referenced, and pulls them all into one single .NET DLL. And each one of those dependencies then from the Java side turns into its own namespace within that assembly so that you don't get collisions within class names and method names and things of that nature. In addition to that, when you actually reference this Hector as .NET assembly, you also have to reference some core IKVM assemblies so that interoperability can actually happen. In addition to doing this, we also wanted to still have another abstraction layer in between there. So we wanted to be able to use Hector in a more .NET-like way. We wanted to have .NET data types and .NET collections and that kind of stuff, and and connection strings. And so we built a wrapper working with Concord to basically abstract some of those complexities or some of those details away, so that we didn't have to deal with Java stuff. We could deal with what felt more like .NET. The other thing this allowed us to do is we built an interface that took the FluentCassandra objects and it sort of exposed those through an interface so that we could switch between Hector and Fluent, because again, we weren't really sure if this IKVM thing was going to work out, and we weren't willing to just completely switch over to it and find out it didn't work and then have to switch back to Fluent or do something completely different. So we built that interface so we could toggle between the two, and that actually helped us out quite a bit because we could run it on Fluent and then switch over to the Hector version and find out that, oh, there's some things that we still need to weed out. There's some things that aren't mapping right to the data types, or certain behaviors that Hector had implemented that Fluent didn't have that we needed to sort of abstract in this Hector net layer that we built. So it allowed us to switch back and forth. And it also allowed us to compare performance. We could see that, hey, when we switched to, when we're running Fluent, we had a certain level of performance. We switched to Hector, didn't really see any performance changes. So that was really comforting to know that this Java code that's essentially running as .NET didn't perform any worse than the Fluent stuff, the native .NET code. So the last challenge that we had to overcome was hooking all of this up to our reporting system. So yeah, we got all this data pumping into Cassandra, all of our activity tracking data, but we need to be able to pull that into our reporting system so that we can actually analyze that data. So our reporting infrastructure looks something like this. We've got Cassandra sitting on the edge, and we need to extract that data out, transform it, and load it into our OLAP system, which is, again, a Microsoft SQL Server. That's a data warehouse, so it's a star schema. And then we pump that into Cube using SQL Server Analysis Services, again, another Microsoft product. So we didn't need to modify between OLAP and the Cube. What we needed to be able to do is get the data out of Cassandra into our data warehouse. And so the point where we needed to solve the problem was in that extract process. So again, using SSIS, which is, stands for SQL Server Integration Services, it's just a way to move data from one location to another. And in the process of doing that, you can manipulate that data structures and whatnot to conform to wherever you're trying to load the data to, transform that data. And so SSIS has what are called script tasks. And script task is just a component that you put into your data flow. And it allows you to write any C# code. You can actually use VB also. I think any of the languages, but lets you write .NET code, essentially. And so because we already had all of this solved for the client side with the web application, which is all in C#, we could plug this in directly into our SSIS package. So we could take those script tasks and write very similar looking code to get the data back out. And so the script tasks have to end up referencing our HectorNet wrapper along with the Hector version of, or the .NET version of Hector that we ported over, and then all of those dependencies that those projects have. So when you're working with SSIS and script tasks, you can't directly reference things inside the script task. You actually have to use that through the GAC. And when you put stuff into the GAC, that means things have to be signed. Well, all of the IKVM stuff and the porting over of the Hector jar file, all that we could easily sign. But we had a lot of our own code that was also incorporated into this, other libraries we had that weren't signed. And so we had to go sign those. And then we find out that something underneath there wasn't signed. And it became this big dependency tree of all sorts of DLLs we had to go sign. And it was a little bit of a challenge, but we ultimately figured it out. It was just a lot of work to find where all of these things were used and update the references to these signed versions. And so there's some challenges there, just something to be aware of if you're going to go down this path. So one of the questions you might be asking, and Jonathan talked about this today, is, well, there's a Csharp driver being released. It's in beta, soon to be going general availability. Why didn't we adopt that? Well, one of the big things is when we started this, it wasn't available. We actually sort of, I think, helped them move that along and said, hey, we really need a way to be able to connect to Cassandra from .NET. You know, what can you guys do to help us? And I think that kind of kicked off their push to get something out there. The other thing, though, is that we're using CQL 2.0, and our understanding is that this driver requires you to use CQL 3, which means changing a bunch of code and potentially even changing some of the data structures underneath, remodel some of our data to support some of those things. And then finally, we just wanted to give a shout out to DataStax. We actually use DataStax Enterprise. Specifically, we just use the support right now. We don't use the Hadoop and Solr integration stuff, but this has helped us out a ton. Being a Microsoft shop, we're used to just stuff working. Not to say that, you know, that Cassandra is a poor built product, but it's in development. There's things that come up. There's use cases that haven't been tested. There's also you know, a lot of moving parts when you're working with a distributed system. So there's stuff that's going to come up and things that are going to fail. And so having DataStax available to have that support has just been a necessity for us to be able to run this. So with that, we'd like to say thanks for stopping by and listening to what we have to say. We're hiring, so if you're interested in joining our team, you can check that out. We do have a Cassandra meetup user group in the Minneapolis area. If you're from that area and you'd like to attend, you can hit up that group on that link there. If you have any questions afterwards of Derek or myself, you can hit us up on these email addresses. And then also, if you'd like a copy of the slide deck, you can get that with this link at the bottom here. And I think now we actually have it, we'll open it up to just any sort of general questions anyone has at this point.
So for the FluentCassandra and Hector net, do you see Fluent moving forward in addressing all those issues that you found? And are you considering going back to Fluent when that's ready? What are your plans in the future for that?
It sounds like the Fluent project, Nick has some other obligations, and so he's sort of not contributing to it as much. He's still the main contributor, but he's actually asked us if we would help contribute to that, but because we've been using the Hector net port, we just don't feel like we need to go back and make that work. The Java community is actively working on Hector, and so all new features are being added to that. It's still a lot of work to keep Fluent up to date, and so we personally just don't feel like it's a benefit for us to go back to that at this point. And ultimately, we'd like to move to the Csharp Driver that DataStax is building. I mean, that's where the future is going to be. That's really where, you know, that's why we chose to use the CQL language, is because we wanted to be as much as possible bound to that, even though it's a different version with 3.0 and there's some changes. It's still very familiar, and we've built all of our application with that in mind. So I don't know if you have anything to add to that, Derek.
Oh, sums it up.
Yeah, two related. Are you actually running Zookeeper on Windows?
Yes.
And so my question is, what are the challenges and issues around doing that?
It's not actually too bad. I didn't do it myself. One of the other engineers actually did it, but it's really as simple as running it in Apache daemon, and you know, there's a few settings, but it works pretty well. Yeah, so we don't have it on every single one of those web nodes, but we don't need it because, like I mentioned earlier in the talk, it's not for every single transaction. It's only for when Snowflake starts up, so it honestly serves 10 requests a month, you know, or something like that. So it's just on, you know, say 4 or 5 web nodes. And so yes, it's set up in its distributed nature, but it's not serving a massive amount of load.
Yeah, and so to that, you know, the only reason there's multiple nodes set up is just for failover, right? If one of the nodes goes down, there's still multiple Zookeeper nodes that can handle those requests. We're not really using it in a scalability scenario.
It does work.
There's a lot of variance on the internet whether it works or doesn't work or it's production ready.
Yeah, we got it to work for what we needed it to. Whether or not it would work for a large scale, you know, distributed system, I'm not sure.
How long your project took from starting from the research to up and running in production?
So we started research last January 2012. Probably spent 4 to 6 months doing just research.
Just you, though.
You know, just looking at different products and then also starting our data modeling, because that's really where you got to start with Cassandra, is data modeling. And I mean, you need to know how to set this stuff up, but setting this up is really not that difficult. You know, eventually you have to tweak a bunch of settings and whatnot, but it's really understanding how you're going to model your data, which really comes back to you need to know your data access patterns. You need to know how your application is consuming that data and start at that point. So, you know, it probably took us 6 months to get to that point, and then we started implementation, which took another 6 to 7 months to actually do. But that's because we stumbled into a lot of these problems with the .NET stack where we didn't have all of the things we needed. So a lot of Derek and I's time at the beginning was spent trying to solve this FluentCassandra problem. And so had we not had to do that and we had a reliable driver to begin with failure tolerance, we probably could have been done a couple extra months early. So.
And what are your reasons? Oh, sorry.
Just to add to that, I mean, there's other challenges not listed here, right? Operationally, as you mentioned, data modeling, training, those things. But we intentionally left that out of this presentation because those are things that apply to anybody that's trying to use Cassandra. So if you need help with that, DataSax is actually, has a lot of training classes, and I know Ben is in the audience here, and he's the one that actually trained Jeff and I on, getting up to speed on how some of this stuff works. And so there's overhead in that too, and that was included in the timeline he mentioned. So yeah, I just thought I'd bring that up.
And what are your reasons to keep reporting sites still in the Microsoft environment? Because that's where most of the companies struggle while processing the data, doing some analysis, running some analytic functions, because Microsoft is slow definitely in running some analytic functions and especially processing the SSAS.
Yeah, I can answer that. So at the time, it was really a matter of focus. So you saw the specs on the SQL Server for the OLTP infrastructure. I mean, we were nearing end of life on that thing in terms of how far we could go. In the meantime, our reporting infrastructure had a way longer runway. And that doesn't mean that's going to stay that way forever, though. I mean, we are absolutely in that mode where the reporting infrastructure is going to have to be a distributed, shared nothing type infrastructure in the future, and we'll be working on that.
Yeah, we're actually starting on that project as we speak. Just last week we sort of kicked that project off to start doing research on what are we going to do to sort of make a distributed reporting system and scale that out. So I mean, if anyone has ideas that they'd like to share with us afterwards, please come see us too. Anyone else have any other questions? Otherwise, like I said, you can come talk to us. We'll probably just hang around for a little bit afterwards, or you can hit up our email addresses, and we'll be happy to answer whatever questions you might have.
And at least I will be at the meetup tonight, so you could catch me there too. All right, thank you.